Now, let us continue our discussions from where we were in the first part of SDN. So, we are now in the second lecture, second part of software defined networks. So, we have already talked about, we have understood the rule placement problem and what are the different issues surrounding rule placement and the TCAM memory, its limitations, and how the rules can be created and how much time these rules are going to be maintained at these switches in the different flow tables of these switches. So, the other issue that is very important is the controller placement problem, and this is what we are going to discuss next. So, we have, just as a recap, we have already in the first part of SDN, we have understood the basic concept behind SDN, the architecture of SDN, the rule placement problem, and the trade off between TCAM limitations, limited memory, TCAM memory, and the delay, and we have also understood the open flow protocol and the flow rule and the math rule, math fields in the open flow protocol. So, in SDN, between the data plane and the control plane, we have an API and another API between the control plane and the application plane. So, the first one, that means between the control plane and the data plane, and that means the infrastructure, what we have is the southbound API, and the open flow protocol is the protocol that is used for the southbound API communication. For the northbound API, this northbound API is used to communicate between the control layer and the application layer, these two planes, control plane and the application plane, and all these existing standard APIs that are used can still be used in the northbound API. There is also the concept of another kind of API which is called the east-west bound API, and this concept, this terminology comes into picture when we are talking about not a single controller, but multiple controllers in the control layer. So, controllers basically define the rule, the flow rule according to the application specific requirements. So, basically what is happening over here in SDN is that the control logic is basically taken care of by the control plane. So, so control logic is separated out, and as a result the controller knows what has to be done with a particular flow, and the controller basically controls the overall flow in the network, and each of these switches what they are going to do, that is done by the controller. So, now going back, the controllers define the flow rule according to the application specific requirements. The controller must be able to handle all these incoming requests from the switches, and the rules should be placed without incurring much delay, and that is important. So, typically so the rules, the placement of the rules, if it is not already existing in the flow table of a switch, typically as we have seen before, takes about 3 to 5 milliseconds, but this has to be minimized, because otherwise what is going to happen is there will be a huge control overhead, and that has to be that, because the controller is being separated out, the control logic is separated out to the controller. We do not want too much of a control linked delay to happen. There is a trade off, definitely, we cannot avoid this delay, but we have to minimize this particular delay. So, typically a controller can handle roughly about 200 requests in a second, and that is applicable for only the single threaded applications, so the controllers which are implementing single threads, but currently multi-threaded applications in controllers are also possible. The controllers are logically connected to the switches in a one hop distance. It is just a logical connection, so the controller from the switch thinks that the controller is away just a hop distance from it, just one hop from it, but actually it is not so. Actually, physically when we are talking about, the controller and the switch can be multiple hops away, and typically they are multiple hops away. So, if we have a small number of controllers for a large network, the network might be congested with control packets, these packet in messages. And so, if we look at this controller placement, there are different architectures, how and where we are going to place this controller. So, one architecture, the basic architecture is called the flat architecture, and here basically the switch and the controller, they are just logically one hop away. The switch sends a packet in message to the controller. If the switch already does not have this flow rule for the particular flow that it has received, so it will send a packet in message to the controller, and the controller is going to send back the flow rule corresponding to that particular packet. That means how it is how the switch is going to treat it. You know, that particular instruction is going to be sent by the controller. The controller knows it. The controller knows how the different flows, how the different packets are going to be handled. This is the assumption in this particular technology, SDN technology. So, this is the flat architecture. Then we can have different other architectures. This is the hierarchical or the tree architecture, and this I do not need to elaborate further, but it is quite obvious. We have these different switches, and hierarchically they are placed with the controllers are placed and connected to these different switches in a tree like fashion, and we have this packet in message and the corresponding flow rule coming back for each of these connectivities. Then we have the ring architecture. In the ring architecture we have a similar kind of thing, but we have to keep in mind that in the ring architecture, so basically these controllers are placed in a ring like fashion. We have multiple controllers like this placed in a ring like fashion, but a particular switch is connected to only one controller in this fashion. So when the packet in request has to be sent, this packet in request will be sent to a single controller only, not that it can be sent to any of the other controllers in the ring. It will be sent to a single controller, and the flow rule is going to be sent to this particular switch that has requested the rule. And then we have the mesh architecture. Mesh, as we know, increases the reliability, and as you can see over here, for instance, we have two different switches who can be connected to a single controller. So, if this one goes down, there is the other one which can take over, and so on. So, it basically improves the fault tolerance and improves the reliability of the network, the mesh architecture. Now, this control, how this control is going to be done, how the control decisions are going to be made. There are two different approaches. One is the distributed, the other one is centralized. In the distributed, the control decisions can be taken in a distributed manner. For example, each subnetwork is controlled by a different controller, and in the centralized mechanism, the control decisions are taken in a centralized manner. For example, a network is controlled by a single controller. So, in such a case, it is a centralized control, and dividing into different subnetworks and having a controller corresponding to it will be a distributed solution. There is also a concept of backup controller. So, if the primary controller is down, then the backup controller takes over. So, the backup controller has a replica of the main controller, and if the main controller is down, the backup controller controls the network to have uninterrupted network management. Another very important thing is through SDN, one can have enhanced level of security in the network, and in this particular case we will be taking help of the firewall, proxy, HTTP, etc., and the IDS, and these can have improved security with respect to this technology. So, just as a very brief, here we are not going to discuss about improving security with SDN in much detail, but just as a brief, this is a paper which was published in SIGCOMM in 2013, very recently, that means, which is talking about the simplifying protocol for policy enforcement. So, what it does, so let us look at this particular figure. So, it is an example of a potential data plane ambiguity to implement the policy chain, this chain firewall, IDS, proxy in this particular topology, and the sequence of flow of instructions is like this. So, it will, this is from the HTTP, when a HTTP request comes, then it is sent from one switch to another switch, this particular switch, then it goes to the IDS, comes back, goes to the proxy and the forwarding and the firewall, and then finally to this particular switch and then to the finally out of the network. So, this is how security is implemented and enhanced using SDN. So, we are not talking about, as I mentioned already, I just wanted to show you that security can indeed be improved with the help of SDN, and we do not want to discuss anything further on this particular issue. So, how do you, so let us say that we have implemented SDN or we want to implement SDN. So, one of the things is that we have to experiment, we have to evaluate the performance through experimentation. So, experimentation can be done with the help of simulators or they can be done with the help of emulators. In emulators, basically what happens, it is little different from the simulators. So, here the real the emulators can be connected to the real network where real traffic can flow through this emulator and the data can be analyzed, the performance of the network can be analyzed using these emulators. Simulators on the other hand basically simulate the entire thing, packet flows, the network, the nodes, everything is simulated. So, these simulators or the emulators take care of few different things. One is the infrastructure deployment, and this must be supported with OpenFlow, and the controller placement which must support OpenFlow. This controller can be a remote controller or a local controller, and in the remote basically the controller can be situated in a remote place and communicated using IP address and port number. A local controller basically does everything is local, the controller itself is local, and it takes care of it locally. For switch deployment, the Mininet software is Mininet simulator, it is an emulator as well. So, it is very useful. It is used to create a virtual network with OpenFlow enabled switches. It runs on Python and supports remote and local controllers, both remote controller and local controllers are supported by Mininet. There are controller configuration software, for example, POX, Nox, Floodlight, OpenDaylight and ONOS. Particularly OpenDaylight and ONOS are the most popular ones that are used for controller configuration. So, with this we come to almost the end of the lecture on SDN, and we have understood the basics of SDN, what is the motivation behind SDN, why do we want to separate out the control logic from the data logic, data plane, which takes care of functions like forwarding etc. to make the network efficient, but there is a trade off as well, and we have seen that more number of control packets are going to flow through the network, but we want to minimize that control logic, and this is where a lot of research is being undertaken at present. And we have also seen that the performance of SDN basically depends on two particular issues, the rule placement and the controller placement in the network. Control message overhead, as I was mentioning before, will be increased due to additional number of packets, the packet in messages from the switches to the controller flowing through, and what is required is to have an unified network management to be made should be made possible using SDN while leveraging the global view of the network. So, we need to have an unified network management architecture or framework using SDN. With this we come to an end of the SDN lecture, and so next what we are going to talk about in another the next lecture is how SDN can be used in IoT to make IoT efficient, Internet of Things efficient. So, we will have to wait for the next lecture in order to understand this. Thank you.